In the last video, we did the first 4 pages, and just to recap about the definitions you need to know, definition of a covalent bond, the idea of these diagrams, displayed formula, well, what you call them, line diagrams or displayed formula, the sort of overlapping shells, the old GCSE dot and cross diagrams, and then we're moving on to Lewis diagrams as well, right? Now, you also need the definition of a lone pair, right? That's a pair of electrons that's not part of the bonding, right? And shared electron pairs are called bonding pairs. Now, I hope I haven't confused you. Here we have, I was talking about these as shared pairs. There are 2 shared pairs of electrons in here, and I said that counts, each of these, for the shape of molecules, counts as a bonding pair. So I might just leave that for now. Put that in brackets. I'm going to just put, that would only count for shapes of molecules as well. It is a double bond, probably just call it that, double covalent bond. And same with this. I think, yes, for the shape of molecules, it actually won't be relevant to this one, as you'll find out, but bonding pair, it is a triple covalent bond. And it has 3 shared electron pairs. Right, but as I say, when it comes to the shapes of molecules, you see this idea of lone pair, bonding pair comes into play. It was really that I was trying to get you to start classifying on that basis. Right, so we're going to move on to coordinate bonds today. Now, this is a new type of bond, right? Newish. It's just a bit of a variation of a theme. Okay, so if you read here, there are cases where both electrons come from the same atom and the second atom contributes none. So remember that it's just, in order for bonds to happen, there just has to be a third pair of electrons, no unpaired electrons, and that can happen. Normally it's where each atom in the bond puts in equal numbers of electrons, but sometimes one atom will put in 2, form the covalent bond with, and use both its a pair of electrons, and the other atom won't contribute anyway. So this is a particular type of covalent bond, right, that's identified as a coordinate bond. So if you look at the definition, it's a shared pair of electrons, same as a covalent bond, which it is, but the only difference is both electrons are supplied by one atom. Now, once they're in the covalent bond, like an electron is an electron, so it won't change anything about the way that a molecule behaves, right? But you just need to identify that the source of the electrons is just one atom for this particular type of covalent bond. Okay, so we're going to look at 2 of them. Now, I sort of described here, but actually I need to give a little bit more detail on this, right? So you're going to have to add to your notes on this one. I think it just needs, I need to show you how it forms. Now, the first thing to note is, if you want to represent a coordinate bond, you just do a line. So that would be a single covalent bond, and you put an arrow at the end. What that arrow says is that the electrons came from here. So both electrons come from nitrogen, and the arrow is pointing to the hydrogen, so they go from the nitrogen and they're shared with the hydrogen. Okay, if we look at the dot and cross diagram, you have each of these, so you've got 4 covalent bonds, right? So there's nothing weird and wonderful about that, and you represent your coordinate or dative covalent bond, as it's sometimes called, your coordinate bond by having the same symbol for the element, for the electron. So you're going to show that both of them came from nitrogen. So nitrogen's original electrons are 1, 2, 3, 4, 5, and each of these is a hydrogen, and this is a H+, and I'll show you how they combine. So make sure you put this into your notes somewhere, right, to show the formation, because I do think it's something I've left out. Okay, so what happens is ammonia reacts with a hydrogen ion, right, form the ammonium ion. Now, if you recognize that, it actually is an acid-base reaction, right, where ammonia, I'm just going to show you where this would come from, plus say HCl, right, would give you NH4Cl plus, what's the other one? No, that's all it gives you. It gives you NH4Cl, okay? Now, that would be from GCSE, dare I say, just triple award. Okay, so you would have done that, but it's an acid-base reaction. So just in case you're wondering any connections. So let's have a look. So this is the ionic equation for that. You've left out your chloride spectator ion, and this is the regular equation. Okay, so in terms of the bonding, let's draw nitrogen, right? And I'm just going to do the Lewis structure. So we've got the nitrogen molecule has got 3 shared electron pairs with hydrogen, okay? And then it has a lone pair of electrons as well. Now, voila, this lone pair of electrons is what's going to form the coordinate bond. If we have our hydrogen ion, let's put a line here. So our hydrogen ion is effectively just a proton, if you think about it. It has no electrons, it has 1 proton and no neutrons, right? So what happens here is these two, this is going to share its pair of electrons with this hydrogen, right? And you're going to end up with this. And then we usually bracket the entire thing, put the positive charge outside. We don't sort of, it depends, we don't always identify exactly what's holding the positive charge, right? The ammonium ion is carrying a positive charge. So remember that that positive charge means that you are short an electron. So just be aware that if you were to count all the electrons you should have, right, you should have 4 from the hydrogen, and if we just look at outer shells, you should have 5 from the nitrogen. So you should have a total of 9 electrons in that particle if it was neutral, right? But you only have 1, 2, 3, 4, 5, 6. You've only got 8 electrons. So it has a positive charge because it's an electron. It has 1 fewer electrons than charges, you know, in the nucleus of the hydrogen and nitrogen, and the protons in total. But it still has, right? It's got all paired electrons. So it's stable. It is stable. It'll attract negatively charged particles, right? But it is a stable particle, okay? Because every electron in the outer shells they're all paired. It ends up with 4 bonding pairs of electrons. In that, whereas this one here had 3 bonding pairs. Move that up a little bit. 3 bonding pairs and 1 lone pair in the ammonia, right? So 4 bonding pairs. Now that will affect the shape of the part of the molecular ion, as you will find out. So this is a molecular ion. It's a, can I remember the definition? It's a group of atoms covalently bonded together that have an overall charge, right? It's the ammonium ion. Okay, so that's one of the most important ones, right? The most commonly asked about. So you have here this kind of energy level diagram, or old GCSE version. Here is the Lewis version. So all you've done is left out the shells. And this is the line diagram. So here you're showing your dative covalent or coordinate bond with an arrow. Here you're showing it by showing that the electrons, the representation is the same, symbol is the same, and that's it. Now let's look at the next one that's very common, which is H3O+. Okay, it's called the hydronium or the hydroxonium ion. It doesn't really matter which name you use. I did search to make sure they mean, I always call it the hydroxonium ion, but I think it's called the hydronium ion in the revision book. So whichever you choose to use, it doesn't matter. Both are correct. Okay, so let's have a look at how it forms. Now, again, this is skipping the actual formation. So we're gonna go through the formation of it. Okay, so formation of H3O+. Now you will see this a lot as the time passes. Okay, so the hydroxyl ion is just, you know, it's everywhere. Okay, so In this instance, what you've got is water, and if it meets a hydrogen ion from an acid, you actually get this substance, this ion, this molecular ion here. Now, in fairness, we often don't even show it. We just show H plus instead. So don't worry too much about the nature of it, but that's how you would form it. Okay, so let's draw the water molecule. Now, in this instance, we have OHH, and I'm going to draw it with its correct geometry. It's a bent molecule. Okay, so you have, right, so you have a shared pair, single covalent bond between the oxygen and hydrogens, and then you've got 4 more electrons. You have 2 lone pairs on the oxygen. Okay, so that's got 2 bonding pairs and 2 lone pairs. Now, one of those lone pairs, right, not both of them for some reason, one of the lone pairs, it meets this hydrogen ion, which remember has no electrons of its own. It can't form a covalent bond by sharing an electron, but it can form a covalent bond by sharing both electrons. Okay, so what happens here is that pair of electrons from oxygen will form a new covalent bond with hydrogen, and you end up with okay, so you've got your regular, if you like, covalent bonds, and then you've got your new coordinate bond. Now, as I say, in terms of they're all covalent bonds, they're all shared electron pairs. All you're showing here is that both of those electrons came from the oxygen originally. Again, you're an electron short, if you count. And yes, sorry, there's still a lone pair on that. So that has 1 lone pair and 3 bonding pairs, right? Why that doesn't form a 4th, maybe it does, no, I've just never seen it. Probably actually because you can't bring another positive charge in. That's it. This would repel another hydrogen ion. Like repels like, so that's why it doesn't form another one. Okay, right, so that's it. You can represent it with the line diagram. Okay, and where's this one is? Okay, so that's the hydroxonium ion. You would need to know that, and yes, oh, I forgot my coordinate bonds. I have to show that with an arrowhead. Okay. Now, it's not always shown, I should say. They will tell you if they want you to represent the coordinate bond, and that means you have to show the arrowhead in everyday sort of use because they all behave equally. Like, it's hard to tell. You couldn't tell from the chemistry of it which of those was originally the coordinate bond. Right, so what you end up with. So here's your Lewis structure. Again, terminology changing. I wouldn't call that a Lewis structure. I'd call that a line diagram. Electron pair geometry. Right, geometry just means the shape. Now, just seeing as it's here, we're not going to have to worry about that too much either. This one here, yes, you are going to have to worry about. This is trying to show that it's 3-dimensional. This straight line means it's on the plane of the page. This solid wedge means it's sticking out, right? So that's a way of showing it's sticking out of the page. And this dashed line means it's sticking back, right? It's going back from the page. So they're trying to represent it in 3 dimensions. We'll see more of that in the shapes of molecules. Okay. Now, once the bond is formed, all right. So here we have. You're going to have to do some practice of dot and cross diagrams. So just like the last time, I want you to watch me do them. I'll work through all of them. And what you can do is just pause, try it yourself, check, or you can watch until you're comfortable. You've seen enough examples, worked examples, and then do the rest yourself. But it's up to you. You do it, don't rush at it. Take your time to master this, and it'll serve you well, at least to the end of A level, and then if you go on to university, beyond, okay? So let's have a look at this. So we've already done the dot and cross diagram of this. Okay, so it's Now, any pedants might think, okay, she's got two dots together. Yes, I mean, it doesn't matter as long as they're different. You represented the particles differently to show that the electrons are, you know, one from each atom originally. Okay. Now, this next one. So, this is an adduct, what's called an adduct. And it's a mixture of BCl3 or BCl3 coordinate or ammonia coordinate bonding to BCl3, boron trichloride. Okay, so what I suggest you do is draw the atoms. To leave space for the bonds. And then we're going to, in the middle, because it's a coordinate bond, we're going to represent it with two dots or x's, it's up to you. And then for nitrogen, then we're going to dot x, dot x, dot x. Okay, so that's the three. So the dots represent the nitrogen electrons here, and the x's represent hydrogen's electrons. So we're going to have to keep these as, and this is going to be x dot, so x for boron. And then we're keeping chlorine as dots. So obviously only have dots or crosses. Now don't forget, if you're doing these Lewis diagrams, don't forget to put in the electrons for the outer atoms, as my own mistake. I get so focused on the bonding pairs and lone, that I forget about certain lone pairs that you will find out don't really change anything. So, but they need to go in. Okay, so it's kind of messy looking, right? You can see why chemists move on to this type of representation, which is much cleaner. Okay, so that is that substance. Now, carbon monoxide. Okay, so you have a triple covalent bond, right? So you've two shared pairs of electrons, two electrons from carbon, two from oxygen, and then a coordinate bond with both electrons coming from oxygen because it's pointing from oxygen. So let's put that in, CO. So let's, we're going to have the dots as carbon, dot and cross from oxygen, dot, cross. So that's the regular, and then cross, cross. That's your coordinate bond. It's a triple covalent bond. And then how many electrons are left? We have 4. We have a lone pair on carbon, very unusual, fairly unusual. Okay, and how many electrons we left? We've used 4 of oxygens, so we have 2 more to go. So we have a lone pair on oxygen as well. So that's the bonding in carbon monoxide. Now, the nitrate ion. Okay, so if you look here, you've got a coordinate bond, and you also have a negative charge on the oxygen. So we're going to talk about what that means. So let's have a look first. So we've got nitrogen. And let's do the double bond oxygen. So dot XX. So we make that oxygen. Okay, so 2 of nitrogen. So that's the double bond. And then let's put the coordinate bond. So they're both, so we've used dots as nitrogens, so 2 more electrons here. Now I've got 6 left on oxygen. So you can see that it's got actually 8, it now has managed to get 8 electrons in its outer shell by sharing both 2 of nitrogens. Now nitrogen has 1 electron left. We've used 4 of the 5, so it's definitely going to be here. And it's a regular covalent bond, no arrow. And now we have 6, we've got 5 electrons left on oxygen, an X, so it's 1, 2, 3, 4, 5. So it has 1 lone pair. I've missed something. Oh, 6, sorry, it has 6. Now, remember I said that you can't have any unpaired electrons. So what does it do about that? Well, this is where the minus charge comes in. It has accepted an electron from presumably a metal somewhere along the way. So let's put that in as extra That's actually black and it's a different color. Right. So it now has, right, it's got a negative charge because it has gained an electron, right? So it's the negative from, say, a metal, presumably. There's not much else can give it an electron. Okay, so it has ended up with full outer shell by becoming negatively charged. So just so you're aware, so obviously we tend to bracket the whole thing with minus, but just be aware that one of the oxygen atoms has accepted an electron so that it ends up with a full outer shell. So just check that you get that, okay? If you can sort of account for all the electrons and see where they come from, you'll be able to work pretty much anything out. Okay, the next one, Al2 Cl6. So you've got two coordinate bonds here. So aluminium, if you think about aluminium, should not, again, aluminium shouldn't be doing covalent bonding. See, if you're kind of either side of this line, you know the way these are non-metals and these are metals, you know, you can imagine that the closer they get to each other, the more the lines blur, right? So like boron and aluminium, silicon and germanium, you know, I don't know, anybody who does physics, you know that they are kind of involved in, oh, I can't remember what it's called, they're partial conductors or semiconductors, that's the one. Right? So they do, like, you know, they do a wee bit of conducting, even though that's non-metal, and yeah, there's just all this goes on, right? And same with beryllium over here, right? Remember, it does covalent bonding, even though it's a metal. Okay, so aluminium, under some circumstances, it does covalent bonding. Now, can I just tell you, if you need to draw a covalent diagram a diagram for a covalent molecule involving aluminium, they will have to tell you it is covalent. You would assume any compound containing aluminium is ionic unless told otherwise. So watch for that. Okay, so this one is, right, so I'm going to put these in first. There's a Cl top. They're the ones that are coordinate bonds, and then Cl. Okay, so let's do, right, so there's a coordinate bond here and a coordinate bond here, and then there's regular bonds. So our X's are the aluminium electrons. Okay, so every aluminium has 3 electrons, so it can form 3 covalent bonds should it have circumstances to do that. And I'm missing this is also a regular covalent bond. And then we'll just fill in all the electrons for chlorines. There's loads of them. So we're using that 1, 2, 3, 4. No, I've overdone it. Right, I'd overdone it. Okay, so the middle chlorines have 2 lone pairs and all the other ones have 3 lone pairs. So the ones that have formed coordinate bonds have 2 lone pairs, 2 bonding pairs, and all the others have 3 lone pair, 1 bonding pair on Cl. Okay. Next, okay. So next bit, I think I plan to go to the end of page 7 or the end of page 6. Okay, so this is just more about coordinate or dative covalent bonds. I've taken this from chem sheets I've discovered. Can be very wonderful. Okay, so this is really actually talking, we've already done this, right? So we've discussed this, just another way of representing it. And now this one is LCl4. This actually, just for future reference, this will come up in A2, and it is electrophilic substitution of benzene rings. Just, it'll appear again in a good while, in more than a year, right? Okay, so what you have here, these AlCl3 is called a halogen carrier. It can be, it's a of catalyst. It sort of activates chlorine, right? Forms, well, we're not worried too much about it. Okay, so if it meets a Cl minus, you get AlCl4 minus. And again, this time, note that the arrow direction is towards the aluminium, right? Because it's the chlorine. It's actually very similar to what we just did. The chlorine is forming a coordinate bond with aluminium. It's using one of its pairs of electrons. And there's an overall negative charge because everything ultimately has to end up with paired electrons, right? Now, so your task now is to try and follow that format and complete these. So BF3 with F minus forms BF4 minus, PH3, which is phosphine, or phosphorus trihydride, you get away with that. This is boron trifluoride with F minus forms BF4 minus, okay? And all you want to do is show it like that. For now, we have to do a bit more work on Lewis structures before we sort of draw the full thing, but you can certainly have a go at including all the electrons. So what you have is, okay, so if you want to pause and have a go at this, and then check yourselves how you get on. Okay, and last task is just to identify lone pairs. You just call them LP, bonding pairs, and number and type of covalent bonds and coordinate bonds in the following molecules. So pause the video and try that, and then check the answers. Okay, now before you watch the next video, right, and this is what I'm going to set for homework then, is I want you to try page 7 of your notes, right? So this is practice in drawing Lewis structures, or you can, as I say, you can do the old GCSE using shells and all that. So I wanted to have a go with that. All right, it's quite a lot of them. So plenty of practice is how you get better. And then I will post the answers, worked answers in the next video.